Close your eyes and imagine Earth 100 million years ago. Towering conifers and cycads stretched skyward, their leaves swaying gently in the warm breeze. The air was heavy with humidity and buzzing with the deep drone of prehistoric insects. In a shallow marsh, herds of hadrosaurs waded knee-deep in water, their tails swishing to scatter swarms of biting flies. The ripples from their steps disturbed schools of small fish that darted away in flashes of silver. Above, a pteranodon circled lazily, its wings casting fleeting shadows over the water. Suddenly, the serene scene was interrupted by a low, distant vibration, a sound felt more than heard. Emerging from the misty tree line came the unmistakable shape of a Tyrannosaurus rex, its massive head swaying with each deliberate step, each footfall sinking into the damp earth with a muffled thud. For over 65 million years, dinosaurs like these ruled the land, surviving cataclysms that would have erased lesser species. They endured volcanic eruptions that darkened the sky for years, ice ages that froze entire regions, and drastic shifts in global climate that turned lush forests into barren deserts. Yet, 6 million years ago, their reign ended abruptly. These supreme survivors vanished, leaving only their avian descendants behind. How could creatures so adaptable and dominant fall so suddenly? The answer lies in a complex interplay of resilience, chance, and a single day unlike any other in the history of life on Earth. Dinosaurs were not a single type of creature, but a sprawling dynasty encompassing hundreds of species across two main branches, the lizard-hipped Saurischians and the bird-hipped Ornithischians. This diversity was the secret to their long reign. Some, like the towering Brachiosaurus, could stretch its neck nearly 40 feet into the air to strip leaves from the highest branches. Others, like the nimble Velociraptor, were barely waist-high to a human, yet armed with razor-sharp claws and keen eyesight for pack hunting. Dinosaurs filled nearly every ecological niche. In swampy lowlands, duck-billed hadrosaurs grazed on tough vegetation using their hundreds of grinding teeth. In open plains, horned ceratopsians like Triceratops formed protective herds, their massive frills and horns deterring predators. In dense forests, small feathered theropods leapt between branches, preying on insects and small mammals. Their anatomy reflected millions of years of fine-tuned adaptation. Some evolved pneumatic bones, making them lighter without sacrificing strength. Many theropods developed feathers not just for insulation, but possibly for display and brooding eggs. Such traits gave them the flexibility to survive environmental challenges that drove other reptiles to extinction. This constant evolutionary turnover ensured that as older species vanished, new ones evolved to take their place. By the Late Cretaceous, dinosaurs occupied every continent and nearly every type of terrestrial environment, from humid equatorial jungles to seasonal floodplains and even subpolar forests. Fire was not rare in the Mesozoic. The planet's crust cracked and bled lava on truly continental scales. Large igneous provinces poured out layer after layer of basalt, sometimes for hundreds of thousands of years. Ash columns lofted sulfur into the stratosphere, reflecting sunlight and depressing temperatures. Rivers ran gray with silt. Fern-prone hills turned the color of charcoal. For plants, these years were famine and reset. For animals, they were tests, and dinosaurs passed many of those tests. In formations like the Morrison of North America and the Chicxulub of China, diverse faunas bracket volcanic layers, which means ecosystems crashed locally, yet recovered within geological heartbeats. How mobility and flexibility. Herding sauropods could walk tens or hundreds of kilometers to new floodplains when their home range failed. Generalist herbivores like Maiasaura likely switched seasonally among conifers, cycads, and flowering plants. Carnivores followed, scavenging or switching prey as abundance shifted. Volcanoes also gave with one hand while taking with the other. Fresh lava weathers into mineral-rich soils, and after the ash settled, landscapes sometimes rebounded greener than before. Fire reset the table, but the diners' dinosaurs kept finding seats. The age of fire bloodied them, yes, but it did not break the dynasty. Say dinosaur, and people imagined steaming jungles. Yet bones and tracks at ancient high latitudes tell a colder story. In Cretaceous Australia and Antarctica, forests grew within the polar circle. The sun vanished for weeks in winter. Temperatures swung toward freezing, and still dinosaurs thrived. Small herbivores like Dinosaurs show proportionally huge eye sockets, an adaptation for low-light foraging. Predators such as Chicxulub, with its peculiar head crest, likely wore insulating feathers to keep heat in. How do large reptiles survive frost and months of twilight? Not by acting like iguanas. Many dinosaurs were likely at least partially endothermic, able to generate and retain body heat. Feathers helped. So did behavior. Some species probably migrated along coastal corridors, tracking seasonal plant growth. Others hunkered down, slowing their metabolism when winter pinched supply lines. Cold snaps elsewhere in the Mesozoic, sometimes triggered by dust veils from eruptions, also pressed dinosaurs. Sea level fell, shorelines shifted, and food webs had to rewire. Yet time and again, new forms replaced old, and the movie kept rolling. If ice and darkness could not end them, what could, over tens of millions of years? Climate is a pendulum. Tropical belts expand and contract. Inland seas spill onto continents and retreat. Mountains rise, wringing rain from the air and casting rain shadows that birth deserts. Dinosaurs rode those swings with remarkable poise. Ornithopods evolved complex chewing batteries as flowering plants spread. Ceratopsians diversified into frilled and horned experiments. Swift, clever dromaeosaurs refined balance and vision for pursuit through patchy woodlands. This was not stasis, but turnover background extinctions offset by originations. When environments opened new niches, evolution filled them. Consider the Late Cretaceous of western North America as climates warmed and rivers braided across broad floodplains. Herds of Edmontosaurus, Pachyrhinosaurus, and other giants spread in astonishing numbers. Predators from nimble Troodon to the heavyweight champion Tyrannosaurus rex partitioned the menu. From eggs and small prey to bone-rich carcasses cracked by 8-ton jaws. Crucially, the tempo of natural climate change, outside of the worst volcanic pulses, left room for adaptation. A forest did not vanish in a day, nor a sea drain in a week. Generation by generation, bodies and behaviors could track the moving target. That is why the fossil record in many latest Cretaceous sites still shows variety and abundance right up to the boundary layer of ash and shocked quartz. The stage was crowded. The lights went out anyway. On the eve of the catastrophe, the dinosaur world did not look tired. Lush floodplains carried seasonal migrations of hadrosaurs that left kilometers of trackways stamped into mud. Ankylosaurs, living tanks plated in bone, swung sledgehammer tails that could crush a predator's shin. Crested saurolophines trumpeted across river valleys. Forest canopies fluttered with small bird-like theropods. Some four-winged gliders like Microraptor testing the boundaries between leaping and flying. Mammals, diverse but mostly small, slipped between roots, scavenging seeds and insects. Plants had changed, too. Flowering species and their pollinators were reshaping landscapes. Along coasts, shallow seas teemed with mosasaurs and long-necked plesiosaurs, while the skies belonged to giant pterosaurs such as Quetzalcoatlus, a giraffe-tall master of thermal soaring. Into this busy, balanced web, nothing obvious suggests a dynasty already failing. Diversity metrics in several well-sampled regions remain high. Juveniles and adults of many taxa are present, Predators carry healed bite marks, evidence of long careers in contested landscapes. In short, the system was working. Food moved from sun to leaf to herbivore to carnivore. Death was constant, but so was birth. This is the moment the universe chose to flick the board. A rock roughly 10 kilometers wide, traveling faster than a rifle bullet, entered the atmosphere over what is now Mexico's Yucatan Peninsula. For a few blinding seconds, it outshone the sun. Then it hit. In less time than it takes to say impact, ocean water and limestone exploded into vapor. Bedrock behaved like liquid. A transient crater opened nearly 200 kilometers wide before the ground rebounded like a spring and the rim slumped. Energy equivalent to billions of nuclear weapons surged through the crust. The first killers were local shockwaves that flattened forests out to distances where the horizon curves, earthquakes that would read as magnitude 11 on a human scale, and walls of water racing outward across the Proto-Gulf. Minutes later came the global killers. Ejecta glass beads, dust, and sulfur aerosols rose into the stratosphere and circled the planet. As that incandescent debris rained back down, it heated the upper atmosphere enough to ignite wildfires on distant continents. Then the long night began. Sunlight dimmed drastically. Photosynthesis faltered within days and failed across months. Models suggest global average temperatures may have plummeted more than 10 degrees Celsius in a season, with surface waters cooling and land plants wilting. Rivers choked on ash, soils lost their grip, acid rains etched leaves and shells. Herbivores starved first. Predators followed not for lack of hunting skill, but because empty stomachs ripple up food webs. Even the air would have smelled of smoke and sulfur. Volcanoes had dimmed skies before. Cold snaps had tested muscles and fat reserves. So why did this catastrophe succeed where others failed speed and stacking? The impact delivered multiple stresses at once, and faster than biological systems could pivot, immediate blast mortality. Weeks of radiant heat, pulses and fire, months to years of darkness and cold. And then, perversely, a greenhouse rebound as CO2 and water vapor accumulated from fires and vaporized rock. Scale mattered, too. This was not a regional eruption with refugees beyond the ashfall. It was everywhere at once. Forests that might have harbored overwintering herbivores burned. Coasts that might have fed scavengers were drowned by tsunamis. Seeds and detritus did persist, but mainly small-bodied, flexible omnivorous creatures able to eat anything, hide anywhere. Breed fast could exploit them. Many birds fit that description. So did some mammals. Giant reptiles with slow reproduction and high daily energy needs could not. There is debate about the role of the Deccan traps, flood basalts erupting in India around the same time. Some researchers argue those lavas and gases stressed ecosystems first. Others find the biggest climate pulse after the impact, not before. Either way, the rock from space was the clincher. It turned a planet of niches into a planet of bottlenecks, and most non-avian dinosaurs could not squeeze through. Extinction is never absolute in a moment. It's a grim gradient. In the soot-dark seasons after impact, survivors were those with the toolkits for famine, small feathered theropods. True dinosaurs we would call birds could fly, or at least flutter between patchy resources, eat seeds that waited out the darkness, glean insects from charred bark, and lay clutches that replaced losses quickly. Crocodilians, with low metabolisms and amphibious habits, rode out the chill in rivers and lakes. Turtles dug in. Some fish and amphibians weathered the change underwater. From those bird lineages blossomed today's 10,000-plus species, a living dinosaur, radiance that fills forests, shorelines, and skies. Mammals, too, stepped into the space left by giants, freed from the shadow of multi-ton neighbors. They diversified, some growing larger, some turning to grazing, others to climbing and gliding. The age of mammals was not destiny. It was contingency written by catastrophe. And yet, look closely, and the dinosaurs are still here. A hawk's talons, a penguin's insulating feathers, a wren's brooding care over eggs all are echoes of theropod ancestry. The line did not end, it forked. What ended was a way of being dinosaur colossal, landbound, energy-hungry rulers at the top of continental food webs. The paradox with which we began has an answer that is both humbling and oddly hopeful. Dinosaurs survived volcanoes, cold snaps, and long arcs of climate change because those stresses left time and space for adaptation. The Chicxulub impact removed both. It compressed disaster into hours, days, and then a few dark years, and it synchronized it across the globe. Evolution is powerful, but it is not magic. It needs generations to work. The greatest dynasty in terrestrial history could not outrun physics.